This is video 2 of topic 8 on water quality and lakes. Here we're going to talk about water quality in rivers and specifically a model of water quality. The amount of dissolved oxygen in water is one of the most commonly used indicators of a river's health. As the DO, dissolved oxygen, drops below 4 or 5 milligrams per liter, the forms of life that can survive begin to be reduced. In the extreme case, when anaerobic conditions exist, most higher forms of life are killed or driven off. Noxious conditions then prevail, including floating sludges, bubbling odorous gases, and slimy fungal growths.
They were the grim scenes that shocked Australia and made headlines around the world. Millions of fish found dead in Western New South Wales.
To me, it was like the coral bleaching moment for the inland. It was an incredible wake-up call.
There were 3 separate fish kills that took place in rapid succession. The first happened on December 15 last year, along a 30-kilometre stretch of the Darling River, near the town of Menindee. Then on January 6 this year, a larger fish kill was reported, along the same stretch of river. That was soon followed by a third event on January 28, again impacting hundreds of thousands of fish, including substantial numbers of threatened species, the silver perch and the Murray cod.
We're going to look at a simple model called a point source plug flow model. This is the simplest model of oxygen resources in a river, and it focuses on 2 processes: the removal of oxygen by microorganisms and the replenishment of oxygen through reaeration at the water surface. The model assumes that there's continuous discharge of waste at a given location in the river, and as those wastes flow downriver, water and wastes are assumed to be uniformly mixed, and there's no dispersion of waste in the direction of flow. In other words, you get this sort of plug that all flows together. That's why it's called plug flow. And so the resulting model is called the point source plug flow model. The model of oxygen levels in the river that we'll look at is called the Streeter-Phelps equation, which dates back to 1925. And this balances the rate of deoxygenation by microorganisms with reaeration at the water surface. The deoxygenation from microbial decomposition of wastes and oxygenation by reaeration are competing processes. The values for this model are given in terms of an oxygen deficit, or D, which is how much lower the actual DO level is than its saturation value. And so here's the initial deficit, so D naught is equal to DOS, so the saturation dissolved oxygen concentration, minus the actual dissolved oxygen concentration at the point we're interested in. And so this curve here traces out the deficit as we move downriver from a release point. Okay, so you can see that it reaches a critical point here, and then it slowly recovers. In the next slides, we'll see how the rate of increase of the deficit is equal to the rate of deoxygenation minus the rate of reaeration. And that takes this form. The change in the deficit over time is equal to this value minus that value, which will eventually lead us to this more complicated looking model, which is the Streeter-Phelps equation. One thing to be very careful about is that D naught and DO are not the same thing. Let's look in more detail at the process of deoxygenation. The rate of deoxygenation at any point in the river is assumed to be proportional to the BOD that's remaining at that point. And so the rate of deoxygenation is some constant times the BOD, which is represented here as L, at the point T, or T days after the wastes enter the river. Okay, so here are the terms defined. And then the rate constant, KD, is often assumed to be the same as the BOD rate constant from a standard lab BOD test. This is actually a pretty reasonable approximation for deep, slowly moving rivers. It's less valid for shallow, turbulent, and fast-moving rivers. Deoxygenation and BOD, of course, are related, as you saw in the previous slide. And so if the BOD remaining after some time t is modeled as a first-order decay, which has this form here, then the equation just becomes the rate of deoxygenation is equal to Kd L naught e to the negative Kdt, where again, L naught is the BOD of the mixture of stream water and wastewater at the point of discharge. This is then assuming complete and instantaneous mixing. We have this form here for the ultimate BOD L naught. Okay, so the terms in this equation, it's just a weighted average, are the ultimate BOD of the mixture is equal to the ultimate BOD of the river, just upstream of the discharge point, plus the ultimate BOD of the wastewater, which will obviously be a lot higher, and then averaged by the flow rates. So QR is the volumetric flow rate of the river just upstream of the discharge, and QW is the volumetric flow rate of the wastewater, which will again be much smaller. So you should expect this to be a small number, that to be a large number, this to be a large number, this to be a small number, and then this one will be the average, the weighted average. You may ask, why are these called ultimate, as in final? The reason is, it's the amount of oxygen that's consumed if all of the weight is decomposed. So if we reach the ultimate point where there's no more waste. Now in terms of the second process, which is reaeration, the rate of oxygen replenishment is assumed to be proportional to the difference between the actual DO in the river, dissolved oxygen, at any location, and the saturated value of DO. And so the rate of reaeration has again a rate constant, and then D, remember, is the dissolved oxygen deficit, which is DOS minus DO. DOS is the saturated value of the dissolved oxygen, so now DO, not D naught, and DO is the actual dissolved oxygen at a given location somewhere downstream. The reaeration constant Kr is very dependent on conditions in the river, and so you want to choose the right value. Fast-moving whitewater rivers will have a higher Kr than sluggish streams or ponds. Attempts to relate the stream parameters to Kr have yielded a number of empirical equations like this. Here, Kr is the reaeration constant at 20 degrees Celsius, U is the average stream velocity to the 1/2 here, and H is the average stream depth. Here are some typical values for the reaeration constant for various bodies of water. If you're looking at small ponds and backwaters, it'll be this type of value. If you're looking at swift streams, almost 1, so 0.69 to 1.15, and for rapids and waterfalls, a much higher value of greater than 1.15. It's also important to note that the solubility of oxygen in the water, or DOS, the saturated value, varies with the temperature, atmospheric pressure, and with salinity. So this table here gives representative values of solubility of oxygen in water at various temperatures and chloride concentrations. So here are the temperatures, here are the chloride concentrations. You can see here as the water becomes saltier, the oxygen content decreases. So we've got 14.6 versus 12, and likewise as it becomes warmer, it can absorb less oxygen as well. So its saturation is 7.56 at 30 degrees versus 14.62 at 0 degrees. Both the wastewater and the stream itself are likely to have some oxygen deficit, and so if we assume complete mixing of the two as we did for the BOD previously, we can calculate an initial deficit of the polluted river with a weighted average method again. That's based on their individual concentrations of dissolved oxygen, and then we have D naught, which is the initial oxygen deficit of the mixture of the river and wastewater just at the discharge point. DOS is the saturated value of DO in the water at that river temperature. DOW is the DO in the wastewater, so W for wastewater, and DOR is the DO in the river water. Now let's look at combining the two together. The deoxygenation caused by microbial decomposition of wastes and the oxygenation caused by reaeration, again, are competing processes, and so the rate of increase of the oxygen deficit here is given by the rate of increase is equal to the rate of deoxygenation minus the rate of reaeration. We've now seen these two equations. They were from slide 43 and slide 44 of your lecture notes. And when we put them together, we can see this oxygen sag curve right here. That equation has a solution that can ultimately be written in this form. The dissolved oxygen is equal to the dissolved oxygen at saturation minus all of this, and this again is the ultimate BOD. These are the rate constants, and these are exponentials. This is the initial deficit. Altogether, this equation is the Streeter-Phelps equation, again from 1925, and it shows that there's a stretch of river downstream of the discharge point where the DO drops rapidly. And so at some critical distance downstream, which is called XC, the DO reaches its minimum and river conditions are at their worst. You saw that on the previous slide in the oxygen sag curve. So this critical distance is right at the very bottom of that curve. Beyond the critical point, the remaining organic matter in the river is diminished, and so reaeration is faster than decomposition and the river begins to recover. Another important equation is this one here. The maximum oxygen deficit occurs where the conditions are the worst at XC, as we learned on the previous slide. The critical time, TC, gives the time of travel to that worst condition location, and it's given by this equation here. The maximum deficit can be found by using this critical time, TC value, in the Streeter-Phelps equation of the previous slide. So you solve for it, then sub it in, and then you can find what the maximum deficit is. This figure is also important. This one shows the connection between deoxygenation, which is this one here, it's a decaying exponential, and reaeration rates, which is here, and the DO curve, which is the second curve down here. What you'll notice is the rate of deoxygenation is much higher here than the rate of reaeration. And so we should expect that the rate of deoxygenation is driving a decrease in the dissolved oxygen or an increase in the deficit. And that's what we see here. At this point, they're exactly balanced. And so we end up with our minimum point down here on the oxygen sag curve. And then here we see the rate of reaeration is actually greater than the rate of deoxygenation. And so we see that there's some recovery here. So reaeration is a stronger process than deoxygenation here, and we go back towards our saturated value of dissolved oxygen. A few final notes on water quality and BOD. The master's text also describes modeling BOD as a first-order reaction, so that looks like this. It also talks more about the reaction rate constant, K, which is here, and nitrification, CBOD, and NBOD. These topics, as you can tell, aren't covered in the course lectures. You don't have to read about them, but if you're interested, feel free to read further on these topics. This is the end of video 2.